Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at what happens when I have to start mixing those orbitals together to make bonds. So when bonding takes place, one of the first problems that we have is those valence s orbitals are really big. So if I'm only bonding with one thing, it turns out almost all the bonding will occur through that s orbital as it's the largest, it's the furthest out, and it's going to be the one that will be most able to mix with the surrounding atoms. However, as soon as I need to start bonding with more than one thing, or I've got extra electrons getting in the way, these orbitals are going to have to start mixing. So if I want to bond with something and I already have electrons in my s orbital, we're going to have to hybridize. So this is essentially a way of talking about what happens when I mix my s orbital with my p orbitals. So when they do this, what ends up happening is that the p orbital starts getting some of the rounded characteristic that we had originally in our s orbital. It spreads out a little bit more, and the s orbital starts picking up some of the p characteristic. It now gains a node, and it is much more unidirectional. But if I'm, say, mixing with a single p orbital, then I'd expect one orbital to be pointed in one direction, the other orbital to be pointed in the opposite direction, because here's going to be the most important idea of mixing orbitals. However many orbitals you have coming in is going to be the number of orbitals you have coming out. And they're all going to be pointed in roughly the same directions. All you're doing is changing who has what character, simply changing not what you have, but where it is. And the type of hybridization is largely going to depend upon what orbitals are being fed in. And one of the ways that we can inform this is by going back to VSEPR, specifically our electronic geometry, because our electronic geometry is going to be telling us a lot about how many different directions our electrons are being pulled into. So let's say that I've got a linear electronic geometry. My electrons are being pulled in two separate directions, which means I'm probably going to have two orbitals coming in. And this results from mixing a single s orbital and a single p orbital to make two sp orbitals. Again, however many orbitals you have coming in is the number of orbitals we have coming out. And you'll always be mixing one s. The biggest thing that tends to change is the number of p orbitals coming in. And we've seen plenty of molecules that have this kind of sp character. So you have simple things like beryllium chloride, or carbon monoxide, carbon dioxide, or even carbon monoxide. In all three of these cases, our electrons are pointed in a straight line. Some of the electrons are pointed this way, some the other way. However, number of electrons pointing in any given direction, this does change. Now, how do we actually generate these orbitals? Well, one of the things we can do is take a look at our orbital diagrams. And beryllium is a great example of this. I've got two electrons in my 2s orbital and no electrons in my p orbitals. However, if I want to mix with two different things, in order to follow this idea of valence bond theory that only partially occupied orbitals mix, I'm going to need to bring one of these p orbitals down low enough in energy that I can put an electron in it. So when I mix this s and p orbital, I'm going to make my two sp orbitals with identical or degenerate energies, which means that the electrons, according to Hund's rule, are going to spread out over these degenerate orbitals, and this will help me maximize the possible bonding. And then the remaining p orbitals are just going to sit up where they were and do their thing. And then I've got two bonding nodes for my beryllium atom. Now, same general idea can apply to carbon dioxide, but now I'm going to have two extra electrons sitting up here in my unhybridized orbitals, and a very similar thing ends up happening with carbon monoxide. So in general, what we're looking at is just trying to mix the orbitals. Some orbitals get mixed into these sp. All the remaining orbitals just stay as unhybridized p orbitals, and we'll talk more about what these p orbitals do in bonding next time. So what happens if I've got a trigonal planar electron geometry? Well, in this case, my electrons are being pulled in three separate directions. So this means I need 3 separate orbitals. So I'm going to take my s orbital, and now I'm going to mix it with 2 different p orbitals. And this gives me a very kind of similar idea. My, my orbital is elongated in a single direction, but now I've got 3 of them, one pointed in each of the 3 general directions. Each of these sp orbitals gains a little bit of this rounded character from the s orbital, but now I have a lot more of that directional character because it has more p character to it. And we've seen plenty of examples of sp2 hybridized orbitals. Atoms with sp2 hybridized orbitals, such as pretty much anything with boron. So boron trifluoride, I've got 3 electronic domains, each pointed in a separate direction, all sitting in a nice even plane. But we also saw something very similar when we looked at, say, carbonate, which is present, as we've talked about before, in baking soda. In this case, I've got 3 different electronic domains, all pointed in opposite directions, as well as ozone. In this case, one of the big distinguishing features is that my electrons don't have to just be sitting in a bond, in a single bond. Sometimes they can be in a double bond, or sometimes they can even be in a lone pair. And let's take a look at what happens when I'm mixing my orbitals for this. So now what I'm doing is I'm going to be mixing my s orbital with 2 of my p orbitals. They're going to become lower energy sp2 orbitals and a higher energy p orbital. Now let's take a look at it more from this energy perspective. So the p orbital energy won't change because it stays a p orbital. Now the sp2 orbital energy is going to be somewhere in between the low favorable s energy and that high unfavorable p energy. But because I have more p character, I'll be a little bit more similar to a p orbital in terms of my energy. And most importantly, all 3 of these orbitals, same basic structure, same identical energy. Only the key difference is what direction they're pointed in. So now I've got orbitals that can undergo bond formation in 3 separate directions. Now, if I'm dealing with something like boron, my p orbital stays unoccupied. If I have something like carbon, I'll have a single electron sitting up here. And if I have nitrogen, I'll have 2 electrons up here, which can undergo some other type of coordination, which again, we'll talk a little bit more about next time. Now, if I have a tetrahedral electronic geometry, my electrons are being pulled in 4 separate directions. So in order to get 4 separate directions, I need 4 separate orbitals. So I'm going to bring in all 3 of my p orbitals and my s orbital, and I get 4 orbitals in, I get 4 orbitals out. And this constructs our sp3 orbitals. Literally, I'm just listing the orbitals that went in. And in this case, I'm going to have an area of density on one side of the nucleus and a much smaller area of density on the other side. And it's going to be this greater density, which has that little bit of rounded s character, but mostly is just a p orbital that got pulled in a single direction. We'll do most of my coordination. And energetically, it's going to be, again, somewhere in between the low energy S and the high energy P, but much closer to the P now, as I'm bringing in more and more of that P character. And this is going to be the type of orbitals that form such classic atoms as methane and most of our organic chemistry molecules, because anytime I have 4 bonds, I'm going to have this tetrahedral electronic geometry and thus sp3 orbitals. So these show up all over the place in chemistry. And so I can either have these sp3 orbitals overlap with, say, a 1s orbital to make a carbon-hydrogen bond, or another sp3 orbital if I'm making a carbon-carbon bond. However, it turns out carbon isn't the only species that forms these sp3 orbitals. Because don't forget, these sp3 orbitals can also be occupied by a lone pair. A lone pair still ends up creating an electronic domain. And in this case, I end up generating, say, a species like ammonia, where I now have a lone pair occupying one of my sp3 orbitals. Because one of the key features here is that, don't forget, all of this is based on the idea of electronic repulsion. And if I have this lone pair, it's still going to repulse my other, the electrons located in these overlapping bonds. So one of the big things to remember when trying to figure out hybridization is, don't forget, lone pairs still count as an electronic domain. Now, it turns out that you can actually even expand this to higher electronic orders, such as trigonal bipyramidal, where now we're being pulled in 5 different directions. However, this means we need 5 different orbitals. So we often do this by invoking the idea that I bring in a single d orbital, which should end up increasing the energy of my hybrid orbitals, because don't forget, d orbitals are much higher in energy than either my s or my p. And this should help generate this trigonal bipyramidal structure. You can invoke the same general idea for a octahedral structure, where now I have to bring in 2 different d orbitals to generate my full 6 orbitals needed for bonding or coordination. However, one of the things that is worth acknowledging is that in practice, we rarely see this d character. And so what's hypothesized, but still not known, is that what happens instead is that whatever atom is being coordinated to, in this case, say chlorine or fluorine, they tend to use their orbitals to coordinate to sulfur. And what we have is something that's a little bit more ionic in nature, where I simply have electrons in that fluorine orbital that wants to be close to the effectively positively charged sulfur. However, this is a good point where there's still a lot of debate in the scientific community of exactly what these molecules look like in this valence bond notation. However, one of the things we haven't acknowledged is, if I go ahead and hybridize and I've got a double bond or a triple bond, I have uncoordinated, I have p orbitals that have not hybridized. Well, how are they involved in bonding? Which is going to be the focus of discussion next time. Until then, take care.